continue now with the heap. I hope we made it clear for you what is a heap in terms of a conceptual level means, a complete binary tree, and now you understand what's a binary tree, what's complete also as well. But the heap has two prior properties, and this is actually, or two kinds, I would say. There is the min heap and the max heap. It is nothing, it's just only the priority of the data stored in the heap. So the heap is a tree, right? I mean, just a complete binary tree. Short, we can call it heap, and we have two kinds of heaps, the min heap and the max heap. The min heap is where actually the parent of every node is actually meaning the minimum, right? It is actually this then as a value, this then has its child, okay? So always from the parent, so then the root will be actually the minimum in all values, then the child is actually a bit more maximum than the parent, then their child is a bit more maximum, and so on. But the minimum is actually in the root, and then every parent is actually the minimum comparing to its children. The maximum is the other way around, where we have the maximum in the node, or the parent node, and its child is this then the parent. Okay, here is an example of a max heap. If you look here, we have some characters, okay, starting from J, I think, and we have H, I, until E, okay. Now, if you look to the order of the characters here, J is actually the maximum, okay. So J coming after H and I. This is a parent, right, for the D, G, for example, is actually coming before H, right? A is actually before I. So you can't find an example here where it's the other way around. Always, if you look to the parent is coming after in terms of the order of alphabets. It's coming after its child. So D, for example, coming after B and C. G after E. Then H after these all. And J is actually after all of these. Okay? So always we store the maximum as a parent, and then the parent is actually the maximum. Then now, this is links us with the priority queue before. The priority queue says that we want to order the data. Okay? We can have such order. Now, if I want to remove something, I will remove from the root, okay? Right? If I want to get the next in the priority, I will just remove this one, the root, J. Get it out. I need them to maintain this as a heap, because if I remove the node, the root, then we have two sub-tree here, this one and this one, how we can link them. This is what we learn in this lecture. We will maintain this again, and next we will actually remove from the root and maintain the heap, and so on and so forth. This is if we apply max heap. Okay. And this is the min heap, for example. This is the other way around. So the parent come first, and its child come next. So A, then B, C, D, E, F, G, for example, and so on. This is called a min heap, and the order based on their priority. Now, question, which of these figures maintain the shape and the order properties of a heap? Because a heap is a binary tree, right? But some of it has two properties, it's a max and min heap. Which of these is actually maintain both the shape and the properties? So what's about the first here? The shape means this one. So we say that complete binary tree is actually all levels are complete except for the last one. It could be actually complete, okay, or could be not complete. So the first one here, maintaining the shape, right? C, A, T, it's maintaining the shape of does not maintain any of the properties. Okay? If we look to C is actually coming after A, but T is actually coming after C. So it's not a max here, it's not a min here. So it maintains the shape, it's actually a heap, but it's not a max or min. The next one is actually maintaining the shape because all levels are complete except for the last one, it's not complete. And it's actually the max heap, okay? And this one is actually maintaining the shape. It's a perfect tree, or can also call it complete tree. And it's again actually maintain the shape, the property is actually a max heap. Okay. Good. Now, this example, because it's coming from the book, I put it a note for you that now we use the one-based indexing to know the parent of a node, the left child, and the right child. And we wrote it here, okay, for you. But it's now in this slide, you can't find it. Okay? Good. Now we start writing algorithms here. Okay, and see the code. Here we have an example. As I said, the data is not visualized like this. The data in our computer is stored in such way. Okay. And I now get node number 16. Okay, it's in position number 1 because we are using one-based indexing now, not a zero-based. Okay, I want to know the child of 16. Okay, here, based on this representation. How I can know the child of 16? Because we have already some formulas, we can know what should be actually stored as a child of 16. So then I want to calculate the left, return to I. So 2 times 1 is actually 2, then position number 2, which contains the value 14, is the left child of 16, and it is here. Now we can calculate the right child. We can say 2I is 1, plus 1 is 3, then position number 3 is actually the right child of position number 1. And you can actually continue with this kind of calculation until you finish all data. And we need this. If we have a data, like for example, if the data is coming like this without actually maintaining any reference, we just have an array. And we want to insert them to a tree, okay? Based on their order. Okay, they are coming from array and they just want to store them. Then I need to maintain a reference for these, okay, initially, or maybe you need to actually, because this is actually, I mean, you are not storing the data as an object, okay, you just have a tree. It is represented as an array or a linked list, but in each element here is not an object, okay, it just only contains the key. 16, nothing else. How I can know my child, for example, then you need to use these formulas again to know the child. But if you store it as a full actually object, then you don't need to use these formulas anymore. Okay. Okay, good. Now I know the parents. I can calculate the left. I calculate the right. We have already explained all of this in the previous slides. The max heap maximum, when we have a heap called A, we have explained it's a good for a priority queue because we have the min max, okay, we can order it. We have immediate access to the highest priority item. Why? Because it's in the root, okay? The next one is always in the root, okay? Just get it from the root. You don't need to ask for it, you don't need to search for it, just get it from the root. Then we have this max heap maximum. In a max heap, getting the maximum element is easy because it's in the root. First, we check if the heap size is less than 1. So, meaning that there is no element, right, in the heap. The tree is empty. Then we actually throw an error. We can say heap underflow. Or we return A at position 1 if we are starting from indexing from 1. Okay? So go back here. We say A1, it actually contains 16, right? Just get the 16. time complexity for this function, for returning the item, is actually 1, right? Look here, we don't have any for loop, we don't do anything, we just call the heap, get the first element from it, and that's it. But if we remove it, the structure is not anymore a heap, right? How we can fix the problem? So, for example, I want to get now J out. The question, how we can actually, if I remove J, because it has the highest priority, it's the maximum. Now I remove that node, we have two subtrees. The shape is not a heap anymore because the root is out. So what is the solution? Now here we can come to the so-called reheap. Okay? So because it's not a heap, we need to do a reheap. Okay? We identify the maximum element, we get it out. We make the next step, says that make the last node in the tree the new root. Where is the last node? Is E in this example. You go to the last level and find the last node in that level and put it as a root. Now, E, we move it from here to here. Okay, but does it actually represent a heap? Yes, it's a heap because the shape is preserved. But is it a max or a min heap? None of them. Okay, because E is actually not, for example, coming after H or I have actually to rearrange now the keys of the nodes so that it's actually a max heap again. And what we are doing now is called reheap down. We get the last element from here and put it as a root, and now I want to move it down until we find the right position for the E, okay, and the right position for the root. What we want to do. So this is the called reheap. Our goal is to restore the order and the shape of the tree. So this is the so-called reheap down. We have here actually a heap phi function. We will explain it, but I will just go with the figures first, and then I will explain it using the algorithm for you. So we get it E from here, and we put it as a root. Now what we want to do, I will compare with its child. Which of them is actually largest? H or I? The largest one. Both of them is larger than E, but what is the larger? Is I. Okay? Then I say, okay, I is the larger. I will now switch or swap E with I. So then I is there, E is here. Okay, good. And because I is the largest of its child, I will not compare I with H. Because I already swapped E with the largest of its child. And all parts here are already maintained. I don't want to check them because I just only get E, which was one of child, okay, and just put it as a root. Though we don't look at this part at all. Just keep reference with E, okay? I switched. Now E is in the position of I. Now I want to look to its childs again. Which of them is larger? F is the larger. I want to switch with F. Then we actually change, and then E is actually become here. F here is I. Then there's no more swaps now. We stop. Now it's a max heap again. What we did is a reheap down. Why we call it reheap down? Because we actually bring the root, the new root, which is actually make the shape correct as a heap, but it's actually not a max or a min heap. Then we start to actually go down with E until finding the correct position for it. And it's now a max heap. How we can do this using algorithms. And here is the solution. This is a pseudocode telling you the steps. Look to the pseudocode. We say first on entry, you need to find out what is the length of I. I is the node that I want actually to B heap down. And this is actually now E in our example. Okay? What is the position for E? Let's say 0. Okay? It's in position number 0. L is the lift of I. What is the position? And here is for people who ask me why we need these formulas. Okay? What is the position or the lift child of position number 0? This is an algorithm. You can't see the tree. You want to deal with the tree as they store. Now you have two options. If you store the node as an object where you can visit it and get, say, for example, I.lift or get lift, for example, then you can get it, right, as a child. And then you can get a reference for it. Now, if you don't store it like an object, you just want to calculate it now. You have the only index of I, so you can say, okay, the lift of I is actually, if you use 0 base, then it's 2I plus 1. If you use the right, the 1 base indexing, it's 2I. Okay? Then you calculate the lift, and you store the index here. What is the lift if we start from 0? The lift is actually H, which is position number 1. We say L is equal to 1. Okay? Not H. We are looking for the index, right? So L is equal to 1 now. And then what is R? R is the right of 0, and it's actually 2. Okay? Then R is equal to 2. Not I. If you have any doubt, just raise a hand. Okay? Otherwise, we can continue from here. We understand each other what we are talking about. The only thing that I want from you to understand that now we are not talking the data inside the nodes, we are talking about their indexing. Okay? So L is the position of the lift child of E. If we start from 0, then the lift is actually H, which is at position number 1. Then I, it's actually at position number 2, which is R. Now we calculate these, but here we don't have the formulas. We have just a function call, and the formulas have been seen in a previous slide where we have defined how we calculate right and left. Okay, good. Now the next, if L, the position here, is less than or equal to the heap size, okay? If it's greater than the heap size, if we are getting an index that is greater than the heap size, that then this index is not part of the heap. Okay? It should be less than or equal to the heap size, so that we are still in the heap, not pointing to a position that's outside. Because look here, for example, if we say that the size is until here, and we have here a position, and we get the index of it, but this is outside the heap, so this is wrong. Okay? Then we continue. The next is actually to compare the value at index L with the value at index I. So we get read AL and check if it's greater than AI. So what we have at AL, H, is it greater than AI, which contains E? Yes, H is coming after E. Then we say the largest is actually position L. Then the largest is actually 1, because H is stored at position number 1. So then again, largest does not maintain the value, it maintains the index of the largest value. Okay, then the largest value is stored at H. Next. If, so we not go through else here, we go to the next if statement. We check if the right is less than also the heap size, meaning we are not exceeding the heap. And we now compare the right with what is stored in the largest, right? The largest is actually, now is the left, okay? So 1, we look at position 2 and compare with position number 1. At position number 2, we have I, which is actually greater than H. Sorry for repeating the information, but I know that some of you maybe understand the figure, but if you go through the pseudocode, you will not understand. This is why I'm just repeating what we have explained in the figure. At position number 2, we have I, which is greater than h at position number 1. Therefore, I have to update the largest. The largest now is not L, it is position number 2. Then largest is actually equal to. Now the question, does the largest equal I? Still the same. No. I is actually 0, right? It is not the largest. So, and largest is actually position number 2. In some cases, maybe you have the node itself is larger than the two childs, okay, when you compare, and then actually you will go here to else statement, you compare with the left. No, it is still greater, then you say the largest is I. You compare with the right, it is still the largest, then the largest is I. There are some cases where the largest is keep as the same node. And therefore, we will not swap anything or update anything. Now, if the largest is not the same I, what we need to do is exchange the value that's stored at position I with the value stored at position largest. In this case here, for example, position largest was I, and this is, contains I, and the I small, which is position number 0, contains E. Now we swap them. Okay? Once we swap them, we recall, this is a recursion call for the same function, we will not stop. This is a recursion. We call the same heap and we send largest. Largest is the index of E. Still, it's 2. I mean, if you remember, we calculated largest was position number 2. Now we send it again and we reheap down. Next, we will call the same function. We can apply it together, but I would not do that because we will compare with the left and then we compare with the right. The left is a greater, therefore we will not go with the right. Largest is not equal to I, okay? Because largest will become actually position number, this is 2, 3, 4, 5. This is position number 5. So largest is 5 and it's not actually 2. Therefore we will do the exchange, okay? We do it. And then again, okay? Send to a reheap. So we will send A and the largest at position says, we said 5, right? 0, 1, 2, 3, 4, 5. Okay, now let's do it again at position number 5. Calculate the left. No left. None. It's actually, we can actually have it as a left based on calculation. Okay? If we use the formulas. If we use an object, we will know that it's none. Okay? But if we use the formulas, we will calculate it and we will get a position for the left and position for the right. But if you want to go to the if statement, compare L with the heap size, the position here is actually after the heap size. Because the heap is actually entered C, position number C. Okay? Therefore, we will say this if statement will not apply, this if statement will not apply. If largest is actually not I, it is still I because we did not update it. Okay? Therefore, we can say stop reheap now. We will not do more. Okay. Good. This is an example that we can apply it quickly together. Okay? Run the max heap file on the following heap example, starting from 4. Okay? We just want to reheap down. We don't want to get our data. We assume that this is a wrong, this is a heap, but it's not a max heap, and we want to reorder to make it a max heap, and we want to start from position number 5. Look to the right side here, 10, 9, 3. It's a heap, right? A max heap. This is sub 3. And here we have 16 is greater than 10. Okay, this part is fine. But this part is not correct because we have 4, 14. No, we have to swap things here. Following the algorithms, we have step number 2. We need 4 was here at position number 2. We look to the left and right. Okay? At the left was actually 14, if you remember. Okay, stored here. And here we have 7. Which one of the largest? The largest is actually at position number 4. We switch. Now we maintain the largest. The largest is actually position number 4. We reheap down again. Okay? Position number 4, look to the left and right. Okay, we have at position 8 and position 9, we have 2 and 8. Now, which one of the largest? The largest value is stored at position number 9. Okay? Now, what we want to do is actually switch. Then we swap the data. We bring 8 at position number 4, 4 at position number 9, as we see here. And then we call the max heap again. But we find that we actually can't reheap down from here. Okay? Then we are done with this part. Okay. Inserting to the max heap. We learned how we can get out things. Okay, we have a max heap, which is the priority queue now for us. We can get the root, and to maintain it as a heap, we can bring the last element, we put it at the beginning, and then we reheap down until we finish. Okay, good. Now, how we can insert to it? We have already a heap now here, and we want to add k. And we have k now here, because we will add it to the next empty position. Okay? And G has, we fill from left to right, right? So G has one child, E as a left child, we need to add K as a right child. We can add K there, but share property is kept, but it's the order property is not, right? You break it. Because now this is not a max heap anymore. Now we reheap up, not down. The same concept that we learned about reheap down, but now we actually bring things up, okay? Because K has a higher value, okay, than its parent, okay? Then we need to bring it up. Okay. K was actually a child for G. We check whether the parent is greater. Therefore, you need actually the index of the parent, and you compare with the value in that index. You find that that index contains J, K is greater than J, we swap. Then look to the parent of K again. And H, you swap them, okay, because K is greater than H. Then you compare K with J, okay, and then you bring it up. Okay, now we finish. Look to this one, it is a max heap again with the new insertion. Now, some of you may say, but this is complex, because reheap down, reheap up when we insert, and we will remove, we will want to reheap down. But if you look, we are not talking about any. How many comparisons we did here and swapping things? We added K, right? K was here. We did it once, and then twice, and then third time. But how many actually nodes actually we have in the tree? We have, until here we have 7, and we have 4 here. It's actually 11. We did not did 11 comparison, okay? Or 11 swapping. Maximum we did 3, okay? And this is actually, if we are talking about a tree that contains hundreds of nodes, millions of nodes, okay? We will actually do this for short time, very short time, comparing to all numbers of the nodes that we have. Okay? And this is what we talk about clock time now. And this is why heap is actually a good for maintaining priority queue. Okay, what we have here. This is the insertion, how we do the insertion, but in text. And next here is the algorithm. I will not read the text, but I will go to the algorithm. The text is just only what we have here. This is the simple code. The only thing that I want from you to understand first is this minus infinity. When we add a node, say K, like the previous example, I will ask you a question now. I want to insert K here, but this is a max heap, and it will not accept K by default, because K is greater than G, and it will not actually add it here. what to do. This is the trick of insertion. This is what we have, why we have minus infinity. Okay? So what we do is that I will say, okay, store k somewhere in a variable x as a value. The value k, store it in another variable, call it x, or let's say value, just for you to follow. I have it somewhere. The value, I have it somewhere. But the node itself, I can add a value, I can add a node with a value called minus infinity. So what is this then minus infinity? Nothing. Then you tweak the algorithm and you add your node with a minus infinity. Okay? That's the first step, to add, force adding that node into your tree. Yes?
So it's similar as using a temporary variable where you need to put the value temporary.
Yes. Yeah. So you store it in somewhere just to remember what was the value of that node, and you trick your algorithm and say it is a minus infinity. Yeah, you can add it. Okay, it's a minimum thing. Put it there, and then now you can reference the value that you have here somewhere and compare it with the parent of the node that has a minus infinity and check. You replace things, you bring things up and up until you have the right node, you can change the value. That's one way to do it. Okay, this is from where the minus infinity comes from. So we want to insert a node into, I don't know if we have an example. Okay, we want to insert a node called x into a heap A with a size n. We first check if the heap size is equal to n. Then we can't insert because otherwise we will make overflow, right? Otherwise, if we did not reach the n, which is the allowed size, we can say now increase the heap size with 1. And now k is actually x dot key. This is where I maintain the value in a variable called k. And don't be confused with the previous example where we added k as a node. Okay? Here k is a variable. You can rename it, call it value. Okay? And we store the value that's in x at that variable. Okay? Like the node that we have, it was x and contained k in our previous example. We take k, x dot key, we retrieve k, and we store it in a value. Okay? Here is the same thing, but it happens that we have this confusion. In the previous example, we have the values also. Okay, whatever. Now, x dot key, we update it and we put minus infinity in it. And then we say that a dot heap size, the last position in my here, add this node that's called x. So we add to the last position. Now map x to index heap size in the array. What is a map here? To define who is the parent and who's the sibling. So we need to use the formulas because we are dealing with an array. When we add the new node, we need to just find out who's the parent and then we have the so-called map heap increase heap. And this is the heap up. Okay? So we will call this function. What we will have here, a, x, and k. K is the value that we maintain. And x is the node itself. And a is the heap, all the heap. So we check if k is less than x dot key, error, new key is smaller than current key. Okay, that's because we start already in x now, we have minus infinity. What could be actually less than a minus infinity? Nothing. Then we bring an error if it's the case. Otherwise, we say now update the key of x with the value that we have stored in the temporary in k. So now x dot k is actually equal k. Okay, finish from that. Find the index I in the array A where object x is occurring. actually the last. I mean, it is actually the heap size now. Now, while I is actually greater than 1 and A, the parent of I, dot key, so the parent of I calculating the position of the parent of I. We get the position, but we don't know what's value inside it. Therefore, we say dot key, okay? Because this is here an object. A parent dot I, we need to calculate the parent of I because I don't know the parent of I. I is the last node in my heap, okay? This is my heap. I is now this one here, or sorry, this one, okay? I want to get the parent, so I say heap parent I. So what is I, by the way? It is the heap size, remember. We are talking about indexing. How I can know the position of the last element in the heap? It is the heap size. The heap size, we can get it directly, okay? Say, for example, 15. Then the heap size is 15, then the last node is actually at position number 15. Now, I want the parent of 15, so I will say A parent I, or the heap size. Okay? Then I can get the position of G. Okay? Back to our algorithm. If we get this, okay, and the key inside it, retrieve the value in the parent, and we compare it with the value that is in the last indexing in I. If it's less than the value, if the parent is less than the value, then we have to swap because then the child is actually greater. Then we do the exchange, okay? We exchange I with the parent, okay? Updating the information maps, priority, etc. This is actually updating who's actually the child of who. Then the references, because now the parent is not anymore a parent of that node. It's a child. So we have to update this referencing. And then I is actually reference to the parent of I. It's a new index. Okay? This is actually the reheap up. The same what we did in this figure. Yes?
I'm a bit confused about the minus infinity argument. Does the system actually realize that when you
No.
put
I mean, it depends if you have. It's a good question again. It depends how you wrote your algorithm. You can actually do it without. But if your algorithm is actually comparing first before adding, which is the thing that you should do, okay? That if you decide that this is a max heap and you want to add something, you first have to compare with the parent. Not just only that we did not reach the heap size, so let's go with this here. I want to add, for example, K, okay? And you ask first whether you reach the heap size. No, still you can actually add. N is actually the last here, and we still have some empty positions, right? Now you want to add K, then the next thing that you could ask, whether compare with the parent, okay? And if it's actually greater than the parent, this is wrong. Okay, you're breaking my max heap, okay? If you do that, then you have to trick your algorithm. You have to maintain the value somewhere else and say that it's minus infinity. But if you don't want, if your algorithm does not have this condition at all, okay, then you just can add it, okay? You just can put it there, and then compare whether you still actually maintain the things. Because in some cases, you can accept only values to be added there only if they may keep the heap maintained. You don't want to reheap things. If it does not keep it maintained, you just, I don't want to, just drop it. I don't know where it could happen, in which application this could happen, that you don't need this piece of data if it is actually, does not actually maintain the share and the property of the heap that you are giving. But if actually you allow for that and you are ready for reheap up and reheap down, then you don't need to have this minus thing. Good. Okay, so now how we build actually a heap from scratch. So we learned about reheap up, reheap down. This is the last thing in this lecture. It's actually, given an ordered array, we have an ordered array here, and we want to build a heap out of it. So what we want to do, first, there is a function called build max heap. We want to calculate maybe the height, I would say, for the tree. Okay. So n is the number of nodes that I can store in this heap. Then the heap size is equal to n. Then I want to now start getting the elements and also performing the so-called reheap down. Okay, if we are building a max heap. But I will not do this for n times. I will do it for n over 2. Okay, and this is why we will do the for loop for n over 2 and down to 1. Okay, for I, the first time we divide n over 2, let's say n is 10, then I is 5, then we call max heap. Go to the position number 5 in my array, okay, and call the max heap. And then in the max heap you compare with the childs, if we remember, okay. Then find the child of position number 5 and compare, do the switching, swapping, okay. Keep do that until there is no swapping. Then you go back to I here in this for loop. You will see this here. So one example. This is the array that we want to actually build a heap out of. It contains 4, 1, 3, 2, and so on. And if you notice, this array is not sorted. Okay? If it's sorted using the max, it's already sorted. It's easy because it's already ordered. Okay? You can just take the node and then position number 0, position number 1 is a child for it, and so on. Just build a tree. But if it's not sorted now, we have to work with it. The heap size is 10 if we start indexing from 1. I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here we use the 1-based indexing in this example. Calculate I. We said we need to divide n by n, the size here, or by 2, sorry. So it is 5. Then the max heap is applied to subtrees rooted at nodes in order. First, A5. The next one is 4 because we need to go from n over 2 until 1. We go from 5 to 4, then 3, then when I equal 2, then when I equal to 1. These are the calls for this function. This function will call max heap in a for loop that goes down to 1 from the first number. The first number in this case was 5, then we need to go to 1, then we will call this max heap 5 times. 5 times from the for loop, okay? But itself, the max heap itself is a recurring. So that's a different story, okay? We will come to it now. Now here is the example. The first step, we go to position number 5, either in the array or I visualize it for you here to just easy understand the things that we have. Okay? So this is position number 5. Okay? Now we call the max heap. What we get? 5 and 8. Find the left for 5 and the right for 5. The right is nothing, the left is actually 10 and it contains the value 7. Compare the value 7 with the value 5, okay? Now 7 is greater than 5, we'll maintain the largest. What is the new largest? 10. Because the largest is the position that contains the maximum value. So the position number 10 is actually the largest. Then we actually do the exchange here in the last step, and then we call the max heap for A and the largest. So we call it for 10, but there is nothing, okay? So we exchange the values, okay? And sorry, here you will not exchange because it contains 16. Sorry for that. So position number 5 contains the value 16. I was not talking to the example. So I will remain actually the largest, right? So we will not do any kind of swapping. So look here, the left is actually position number 10, the right is nothing. We need to do a comparison. 16 with 17 is actually not large, so else largest is actually equal I. Okay? Then we keep actually largest at position number 5. We will not actually go for the recursion. Now we go back to the for loop, right? Remember. Now we go down one step. We call it down for a max heap A and 4. Okay? This will be the next step at position number 4 here. And we apply the same algorithm. We find the left and right. The largest is actually at position number 8. So what we want to do now, we want to exchange them, right? So we exchange the values 2 and 14. Okay, as we see in the third step, they are already exchanged here. But the largest is now, largest as index is actually equal to 8. Because it's the index of the largest, right? Before swapping, we decided that the largest is as position number 8. Now we swap 2 and 14, and we recall the max heap as a recursive for A and position number 8. But position number 8 has no more child. Therefore, we will maintain 8 with 2 as a value, as a largest, and we will not call itself anymore. Then we go back to the for loop. We call it for 3 here. We look to the largest, and we find that 7 contains the largest value. Then we actually change, and then we call the max heap recursively for 7, position number 7, but has no more child, therefore it will finish. Then we go to the for loop, and we call it for 2, and we do the same. Then for 1, again, we compare with the child 16 and 10. We find that 16 is the largest, and we actually this is, yeah, we compare at 4, we compare 4 with 16 and 10, and we bring, this up, we bring this is correct, and this is at position number 3 here, was actually 9 and 10, then at step 4 we have 10 as the position number 3, that's correct. Then we actually look at position number 2, okay? At position number 2, we have 1, and we call it for 1. Now what we want to do, we look to this here. 14 and at position 4 and at position 5. At position 5, we have 16, and which is the largest. We actually do the change, right? So 16 become at position 2, and 1 at position 5. Okay. Now we also reheap. I mean the recursively. Okay. So position number 5 contains the value 1, and its child is actually position number 10 contains the value 7. Now we switch again. So we will have 16 here, 7 and 1. So if you look, this one will call recursively itself until 1 is here. We will not finish because the for loop here says we are at position number 2. And we did it now, still we have to call it for 1. Then we go for 1, and we do the same. Then we have 16 up. Because here we have 4. What we will do is actually replace it with 16. 16 will come here, 4 will become here. Then compare it with 14 and 17. 4 will become the position of 14. And then 8 will become here, and 4 at position 9. So that's the last shape, okay, of the heap. It will take a lot of time to do that, but not if we do the comparison, number of comparisons that we did is actually, and it's actually equal to big O log n as maximum number of comparisons. Okay. Any question about max heap, in heap, priority queue? Okay. Good. Then thank you for your attention. You can stop here and then you can start. sizes.